Hello, everyone. It's my pleasure to introduce Professor Bud Mishra. He graduated from CMU with PhD in computer science. And now he is a professor in NYU in multiple departments, including computer science, mathematics, engineering, and school of medicine. He is a fellow of IEEE, ACM, and AAAS. His pioneering work including hardware verification with model checking, reactive robotic hands, and single molecule nano mapping, and cybersecurity with biologically inspired algorithms. Today, Professor Mishra will talk about science and art of deception in biology and technology. Let's welcome Professor Mishra.
Thank you. Can you all hear me? I have to admit to a deception. The picture of me you saw is the real picture. I'm just standing in for a real Bud Mishra. So I don't look anything like the picture anymore. That picture was taken when I came to CMU by my second or third day. So I've lost hair and changed, but it's a nice deceptive picture. So I'm going to tell a story, lots of little stories. Some of it will be technical, some of it will be biological. But if you have any questions, just raise your hand and we'll go through that. How many of you are computer scientists? All, right? Yeah? Mathematicians? Game theorists? Philosophers? Okay, so we'll touch on a lot of different things. So I want to start with a really big picture. So this was a cover of Time magazine. And Bill Maher said the truth is dead and the internet killed it. So if we played any role in developing or inventing internet, we should take some credit for killing the truth. Somewhere along the line, the internet became bullshit boulevard and the truth became roadkill. So, so how did this happen? How did we manage to do that? We actually started thinking about deception in technology around 6-7 years ago, and we thought it was important enough to actually patent it. So I'll talk about the IP that we hold in mitigating deception. So there is a paragraph in the patent that says what will be your survival strategy. The solution of migrating to another planet or country. I'm sure a lot of people are thinking about it now. It's not a very good idea. Not using the web, another idea. Being anonymous, using HTTPS, or using encrypted information in your messenger or texting and all that. Those are some of our choices, but they will only provide temporary relief and will address minor annoyances. We need a better solution. So here is a picture of a planet. It's an exoplanet called Kepler-22b. It orbits a G-type star, Kepler-22, and it is Earth-like. So if you are thinking of not just moving to Canada or Europe, you could go to this planet. So I have a series of questions for you. On this planet, will they have RNA, DNA, and protein? Will the life form look similar to ours? Right? Will it satisfy Crick's dogma? Will it have genetic codes and codons and anticodons the same way we have? How many of you think it'll be similar? Okay. Can we find multicellularity, multicellular alien life forms on that planet? Our multicellularity only came about 1 billion years ago, and through Cambrian explosion, and it happened in multiple ways. It's a divergent evolution. We got metazoans, animals, plants, fungi, green algae, blue algae, We created symbiosis with mitochondria. Plants created symbiosis with chloroplasts. So it's a complicated process. Will this planet have that? Will they look anything like us? In their body plan, will they have mouth in the front and anus in the back? That's a very important biological question, right? So there are ortholog genes, BMP and anti-BMP. They structure the dorsal ventral. They are the dorsal ventral morphogenes. In lobster, it works exactly opposite. Our first orifice of origin is anus. For lobster, it's the mouth. So there's a big tube that connects the mouth to the anus. How does it get created? Whether you get vertebrates or exoskeletons depends on how DMP, BMP, and anti-BMP are interpreted. Our anterior-posterior morphogenes are very, very precisely preserved, and we have bilateral symmetry. So there's nothing much going on in that. So will this planet have the same body structures? And this is usually called the Cuvier-Jeffrey debate. And this is about, it happened around French Revolution. And we now know that Hilaire-Jeffrey was actually right. And he figured out that lobster is just an inside-out us. Okay. So will this planet have multicellular structures, and will they look like that? How many fingers? Will they have feelings? Will they have central nervous system? That's an important structure in the anterior-posterior system. Will they have limbs? Will they have fingers? How many fingers? And that was a big debate. Physical anatomist Richard Owen, one of the most famous biologists in England before Darwin, assumed that there's an archetype that's pentadactyl tetrapods. We'll have 4 limbs, and each limb will have 5 fingers. But that turned out to be false. There are Ichthyostega and a whole bunch of other animals we found that had 6 fingers and 8 fingers. So will that have that? Will they say klatu barada nicto? Will they have language? Will they speak? Will they have clicks in that language? Will they have universal grammar? Right? So these are also interesting questions. Will they trade gold kryptonites? Will they record the transactions on a crypto ledger? What kind of financial, economic systems will they have? So it's not that easy to just move to another planet. You have to think about all of these questions. In Elohim, will they trust? Will they have a religion? Be monotheistic, polytheistic? What kind of things will they have? These are very interesting questions because we can't really derive them from quantum mechanics and physics and chemistry. There's something else going on, right? Will they have a theory that multicellular life could have evolved on Earth about 1 billion years ago? So the point of all of this is that none of this is guaranteed by physics. They're all conventional. They're conventional equilibria, very stable conventional Nash equilibria of a game. What game is that? And why is it stable? And as we go forward, doing internet and coming up with our protocols and all those, are they conventional? And which convention will stick? And will they be good conventions? Right? So a lot of the questions about cybersecurity, governance, economics, religion, all of those things can be asked as a big question of this kind of games. Okay? So, so I'm going to talk about that game. It's an information asymmetric game, which is fits in with classical game theory, but it is not information complete. Not all parties have access to the same information. One of them is informed, and other one is uninformed, and they need to play a game to coordinate. Right? So language is a great example. I mean, as Chomsky would say, it's not for communication. It's to establish certain kinds of regimes where community can work. A lot of it is about gossip. A lot of it is about establishing social orders, social grooming. There's a social component to it. And also language allows huge amount of deception. Those of you who have children, the first time your child figured out at age 4 or 5 that he could lie, he could tell you that he has a stomach ache and can't go to school, he is using information asymmetry. He knows that you have no way of checking whether he has a stomach ache. So I'm going to talk a little bit about signaling games and how we control risks and deception. Okay? So this is quite old. First paper is probably around 1973 by Spence, and then Zahari, David Lewis, Sobel. They have all written about it. Most of it is in the context of economic systems. There are job market games. There's lemon market games, when you buy used cars. So in economics, there are lots and lots of examples of these kinds of signaling games. But it's not as widely used to think about technologies we develop or to understand biology. And so it's really a fun area to think about. So two-player games with incomplete information. One player is informed, the other player is not. The informed player's strategy set consists of signals contingent on information. So he's going to send a message or a signal to the receiver, and receiver has a set of strategies that consists of actions contingent on signals. You want to go from place A to place B. You know that information. Your Uber driver does not know that until he accepts your signal that goes through Uber. And of course, when you get in the car, then only he knows where you're going. But Lyft has a different convention, and Ola has a different convention. So question is, why is that there? And then at some point, there was no information to you about surge pricing, but they changed that. So there are mechanisms in this game that we need to understand. But there are many, many examples. Internet, I'm going to argue that internet wouldn't exist if there was no information asymmetry. If Google tells you that you should give away all your information because if you have nothing to hide, you should not hide anything. But don't trust that. Don't believe anybody who says we do not do any evil. Sometimes they do a little bit. So how much of that deception exists is an interesting question. So the game we'll talk about is between sender and receiver. And I'm going to introduce a few more non-strategic players. They will be called recommenders, and some called verifiers. I'll call them Rekha and Vera. And Rekhas and Veras are non-strategic. So they will, recommenders will maintain liveness conditions by introducing more and more types. And verifiers will constrain with reputation systems, trust systems, and so on and so forth. So they are assumed to be non-strategic, but if they're strategic, there is an issue. Also, you can think of biology in terms of recommendations and verifications. Recommenders are variations in your genotypes, which does not know the phenotypes. And selection is a selection on your phenotypes. And there is a one-way function through Crick's dogma or Darwinian selection that takes the information from genotype and converts into phenotype. Okay? And the equilibria. The evolution dynamics is to maintain equilibria and moves through that. It's not survival of the fittest. It's not really optimizing anything. It's a struggle for existence. Right? So it's not necessarily optimizing some fitness function. It's just making sure that the recommendations that are verified survive, and you are in the struggle to exist. Is that clear? So that's why I find this very interesting. So the question is, how do these things get organized? On the internet, will we have a Darwinian evolution systems with lots and lots of recommenders recommending new techniques and disruptive things? And some of the disruptions will stay, and some disruptions will go away. And are we converging towards something that's good? And we're already struggling for existence in that environment. And like multicellularity, like language, it hasn't yet stabilized. But it will probably stabilize in our lifetime. And we have a chance to understand where we are going. Yeah? OK. So let's make it a little bit mathematical. So S will stand for sender, who is informed. R will stand for receiver, who is uninformed. Roles can be shared because there are partial informations, and actions are distributed. Not everybody can do every action. not all information is available to all. So the real goal for internet is to find and match and create structures to bring out equilibrium. So think of internet as a correlating device, right? So it's not all Nash equilibria you're getting, but there is actually some sort of correlating device that's making sure who matches who pays who does what action. So there is a random variable t whose support is given by capital T, which is a set. We'll call those types. So senders have types that are assigned to them by nature. Right? So my gender, my height, my annual income, they're all assigned to me by nature. And I'm going to not reveal all of those. I mean, it's hard to not reveal my gender and my height if I'm giving a talk. But on the internet, I'm going to hide those things. So I need privacy. I'm going to be behind a veil of ignorance. And the system is going to support that, going to honor that, and not break my privacy. Right? And I will also decide who I interact with. There's a correlation of encounters. Some players I'll go back over and over and over. Some players I will abandon immediately, and that's the trust system. So privacy, trust, security will have precise meanings in this sense. So maintaining information asymmetry, maintaining correlations of encounter, all of these things are well defined. Okay? If the system was completely transparent, then of course I have nothing to talk about because it's not an information asymmetry game. And if everybody is truthful and everybody is transparent, that's a classical game, and that has very different kind of equilibria. Any questions so far? Does this make sense? Yeah? Okay. So player S learns his type T. S sends a signal from a vocabulary called capital M. So capital S sends a signal S. R takes an action A, little a, in the set capital A. For our purpose, we'll assume these are discrete sets, but you can generalize that to continuous variables in intervals or some compact convex space. But let's stay with discrete finite sets. Yeah, okay. And once a game is played, there is a utility function. So the sender gets a utility, right? So the person who's being driven by a Uber driver has his utility, and the Uber driver, based on the signal and the action he takes, gets a utility. And the type of the passenger still remains unknown to the driver. But they can see the picture, they can see the first name, they can see the driver's license and the number, but most of the information is still intact. Yeah? In fact, the driver will not recognize me the next time he drives me. So, and these utilities are not necessarily aligned. So it's not necessarily clear that for the same type, same action, both of them will actually optimize. In fact, it becomes more interesting when they're misaligned. Okay? Given the structure of the game, you can define behavioral strategies that are distributions given as conditional probability of sending a signal given a type T, or doing an action given a signal. So alpha and mu are those distributions, and sender and receivers are going to choose some distributions. Those are their behavioral strategies. So that defines a distribution on the strategy profiles. Remember that the receiver actually does not know what the true types are, true distributions are. But if he repeatedly, continuously interacts with you, he will develop a subjective probability. Right? So, and the subjective probability will be dependent on Muse and alphas. And then you can write down a Bayesian game, and it will have, for very natural reasons, it will have a Nash equilibrium. right? So they will reach an equilibrium. There could be multiple Nash equilibria. They will reach one. That's guaranteed. It doesn't matter what you do. And at that equilibria, the receiver will have a subjective probability distributions, and the sender, if he plays repeatedly, also will have a subjective distributions of what subjective probability distribution the receiver has. So it's sort of a common knowledge kind of situation. Right? Those subjective probability distributions are not going to be the true objective probability distributions. There's no guarantee. It simply says there is a Nash equilibrium. In the Nash equilibrium, receiver will think that the types are distributed this way. You have some sort of ideas how many Ukrainian hackers are there, how many Chinese state hackers are there, how many Russian trollers are there, but that may not be the objective probability. Right? Iran may still not know who made the Stuxnet, but has a subjective probability distributions. Based on that, they will act with Aramco hacks, and US will have a subjective distribution of what subjective distribution Iran or North Korea has about how US acts. So that's the sort of the combined reality that we will work in. Is that making sense? Right? And that's what, as a software engineering institute or developer of internet, that's what we are interested in. Right? We're not really interested in creating subjective probability that perfectly matches the objective probability distributions, but we want to know where we are. Right? So it generalizes the idea of knowledge and common knowledge. I may know I'm good, and I'm interacting with people who are good, and the people I'm interacting with know that I'm good, and I know that they know that I'm good, and et cetera, et cetera. So the kind of common knowledge is encoded in these distributions. Okay? So now, there may be some kinds of hidden natural functions that we are trying to achieve. So sender, when he has a type T, he wants a receiver who does an action that matches his type. Right? So I want to join a university as a professor where the students have certain type. The students, on the other hand, they have a particular goal. They may want to have professors that have certain type. So it's possible that I want students who work hard and get good jobs and develop startups and give me equities and develop unicorns, et cetera. The students may have a function that says, I want a professor who writes good recommendation letters and gives me good grades. So these are not necessarily the utilities that are matched. Right? But we are in the same place, and we have to figure that out. So I'm going to suggest a utility function that has two components, which is one is a rate function. So I want to work with as few messages, as few signals as possible, but that's consistent with my types. So this is the mutual information between my types and the messages I'm using. And given that I work with those messages, there will be some action that will take place, and I want to see how distorted they are from the actions that I'm expecting. So that's the distortion function. So this is written like a rate distortion function, and one of the parameters is the Lagrange parameter lambda s that says how much I'm going to swap, trade off rate versus the distortion. In some cases, I may not want any distortion. I want a rich message space where there's zero distortion. So if I'm using a legal systems or a payment systems or healthcare systems, it may be necessary that I use very complex message sets, lots of written documents and records and blockchains and all sorts of things, so that the rates are high, but distortions are low. Okay. Same thing with the receiver. They may also understand that they can interpret messages and map them to actions using small number of messages, but they also want to make sure that they are doing actions for the right type. They want to minimize distortion. Okay? So unlike most of game theory, I'm imposing these as my utility functions. Okay? And then the receiver has a subjective probability. At the Nash equilibrium, there is a subjective probability. And if I am an outside observer, I can compare them and see how far apart they are. Right? That's the Kullback-Leibler divergence between these two distributions, and that's what I'm calling deception. If the Kullback-Leibler divergence is 0, that the objective distribution matches the subjective distributions, then there is no deception in the system. But I'm not really looking for a completely deception-free system. I want a system that actually satisfies many of the goals. Okay? So we'll come back to that. And I'm going to look at biological systems in that context also. So just to summarize, every type T sends a different signal for M sub T. Those are called separating equilibria. So there is a one-to-one map or some sort of bijective map that separates my messages from, that matches my messages with my signals and actions. Those are considered very, very good. A perfect separating equilibria would be every message I send is consistent with a type, and every action is consistent with the message, and the type and actions match. But we're not necessarily giving that. Pooling equilibrium will be every type T sends a signal, a star, a single signal, and the action is always the same. And then there are babbling equilibria, where the sender babbles, sends random messages, and actions are random. Those are all Nash equilibria. So if I'm going on a web page, I get a random ad, I randomly click or not, those are babbling equilibria. If I'm going to be shown an ad and my action is always the same with an ad blocker, that's a pooling equilibria. A good separating equilibria would be I see an ad that I'm interested in, and I click, I find out information, and I buy. Perfect conversion. Right? So that would be the ideal advertising thing. And the question now will be, with real-time bidding, with DMP, digital data management plans, SSP, DSP, the structure we have built around ad exchanges, how far is it getting us to a good separating equilibrium? Yeah.
So does this model capture people's ability to learn about what the other person has learned about them? So
yes, right. So the question is, how do they do that? So the question was, do I allow multiple senders and multiple receivers to learn each other's information? Is that the question? No. Go ahead.
Well, I'm thinking more about people, if they notice that they're getting targeted ads,
right.
They've realized that the ad provider has learned something about them.
Right. Right, but how do they act? How do they react to that is the interesting question, right? So some of the things that we'll talk about, the way they will interact with each other in a distributed way would be through recommenders and verifiers, right? So there could be a recommender that could say, these are clicky, baity ads created in Macedonia by KGB or FVR, whatever, don't go there, right? There could be verifiers that can say, or I can tell Google exactly what areas I'm interested in. They'll make sure only those ads I see. But then I have to trust that Google is actually a good conduit to share this information. Right? So there are DMPs, the data management plans. They are actually the recommenders right now. They put a cookie or a super cookie, and when you go to a page, they know, or they pretend to know whether you're male or female, whether you're a soccer mom, what's your income, and if you will tolerate a differential pricing. Every time you go to a hotel room, the price is matched to your income, et cetera, et cetera. But you may not like differential pricing. You don't want to pay more just because you are you. So there are all sorts of conflicts that come in these kinds of games. Right? So for example, Uber drivers are not allowed to share information. Uber does not share the aggregated information among those drivers. Can you create new systems for Uber drivers so that each time they find somebody, do something, they post it or comment on it and create a reputation for Uber. I had a serious experience with Airbnb in New York, in Pittsburgh, and they simply did not allow me to post, but we fought them. And so these are questions. The questions are we losing enough bargaining power in the system to be able to share our information? And how would you address that? Yeah? Any other questions? Okay. Okay, sorry. So these are the kinds of equilibria you get. And there is deception in the systems because there is information asymmetry. Since I have privacy, I can say whatever I want to about who I am. Right? So if I'm a millennial, all millennials are called Esther. They live in Staten Island, and they're 90 years old. And they post pictures about drunken sprees. So that's one way to fight it. Right? Is that clear? Okay. So, but it's not any different from your 5-year-old pretending to have a bellyache. Right? So if everybody does the same thing, then the system can be defeated. And the question is, do we want an internet where we don't have anonymity, but we don't have privacy, but we have ability to deceive you? You build an AI system, you release it on the internet, it's called Twain, and all the millennials gang up to teach it to be a racist and make stupid remarks, and then Microsoft has to take it down within 24 hours. So that could be an end to AI. Or I'm Ukrainian, I screw up Google Translation. Every time it sees Russia, it translates it as murder, and every time I see Putin, it translates it to evil Satan. Right? I can teach Google Translation System a new version of Ukrainian to Russian translation. Right? So it's not, deception is not just limited to Google and Facebook or Microsoft. All of us are participant in that. Okay? All right. So, but this is what we know mathematically. And we know that we don't want to play this game because if we end up with a babbling or pooling or some combination of those, that's not the purpose of burning large amount of cloud and server time to get there. So it seems very useless way of building a technology. Right? And it has nothing to do with whether we're humans, we have bias, we think fast or think slow. It is really the game. That's where we are actually rational, and we are getting this equilibria because we are rational and we are interacting strategically. Right? It has nothing to do with whether we are doing satisficing, whether we are Bayesian, we have biases. So, so that's my assumption. Is that clear? Okay. All right. So signaling game in biology. So I like this picture. It's actually a picture from Roger Penrose, and I stole it. Okay, I'm going to speed up. So there is a physical world that has all sorts of elements. There's carbon, nitrogen, etc. So a small part of that universe, carbon and nitrogen and phosphate and sugars, that will create long polymers. That's what I'm going to call symbolic world. Right? Those are polymers like DNA, RNA, proteins, made of amino acids and bases and etc. Not all of those strings will make sense. They'll be total junk. A small part of it will be genomes. Okay. That's the small world. And out of those genomes, they will build multicellular structures, brains, and books, and music, and so on and so forth, and map how to map DNA to RNA to proteins, etc., connect which neuron to which neuron, and they will write books. Most of it will be garbage. But a small part of it will be about gravitation, quantum mechanics, dreams, psychology, etc. And that small part is going to try to describe the entire physical world. Right? You start with physical world, you take a small part, do something, take a small part of it, do something, and you're back. Right? So how does that process get to equilibria so that we have a grand unified theory of quantum gravity that's based on natural neurons or artificial intelligence, and so on and so forth. So that raises the question about how did this thing come about? How did the universe start? How did life start? How did intelligence start? Right? How do these mappings come about? Okay. So let's look at origin of life. So this is a signaling game that's about 3.5 billion years old. There are two players, messenger RNA and transfer RNA, mRNA and tRNA. So they lived in an RNA world. It was syncytial. All the RNAs talked to each other, et cetera, et cetera. But the RNA world got invaded by very toxic objects, amino acids. So if you think about biology, biology's goal is to keep water molecules in good arrangements, H2O, and they control its pH conditions, the ions. They have ion channels. They have layers, membranes, which is hydrophilic and hydrophobic. So it's all about water. And if H2O becomes hydrogen peroxide, they die. Okay. So the idea is to keep water, and never let it be hydrogen peroxide. And some of the early big proteins like catalase, the main goal is to keep the system out of developing hydrogen peroxide. So into this world, I send these 7 kinds of amino acids from somewhere. These amino acids are going to be highly toxic. So what do these guys do? They have a new job. Job is to figure out how to string these amino acids so they develop hydrophilic, hydrophobic structures. They go into conformation to soluble proteins, get dissolved in water, and get out of the system. If they string together monomers, same amino acids over and over and over, that doesn't work. That will not fold. So they have to be more clever. If they just string them together randomly, that also will not fold. So, sorry. Thank you. Okay. So what they have to do is to figure out a particular ways of connecting these amino acids so that it has a good secondary structure. Okay? So they need to talk to each other and come up with a good separating equilibria that gets rid of soluble proteins. But they will get clever. They'll figure out that they can actually fold other things and make proteins that have enzymatic reactions, enzymatic properties, and they will then use that for structural things, for transcription factors, all sorts of things, right? And then if those mRNAs, the strings that are doing the right thing, are good, they're actually going to remember them. How do they remember? Using double-stranded DNA. So they have to come up with RNA. From the RNA synthesis world, they have to play this game and very quickly figure out how to create DNA, proteins. So think of DNA as a blockchain. It has to be immutable, can store the good actions, and could be inherited, et cetera, but they are going to coordinate how the mRNA and tRNA are going to interact to string the amino acids to do good enzymatic reactions. So that's where the most interesting thing in life starts. If that hadn't happened, we wouldn't be here to give this talk or listen to this talk. Okay, so in 1953, Miller and Urey did an experiment of how this would come about, and they figured out a whole bunch of amino acids. Actually, there are prebiotic amino acids, but there are also synthetic amino acids. So life itself figured out how to make new amino acids, and in the process, they created a language which is keeping them in Nash equilibria. Those are the codons. Codons are anticodons, and they are conventional. That means you could have come up with other codon anticodons that would have worked equally well. So, but they are universal. All of us, plants, animals, metazoans, single cells, we all have the same RNA, same codons, same anticodons. There are some exceptions. Some have 21 amino acids. Some are missing some amino acids, like mitochondria. Some fungi have extra amino acids. But more or less, we are universal. Right? Life is universal. They use the same Nash equilibria. It's immutable. It is actually very error tolerant, and it has a Shannon entropy that's close to optimal. And it hasn't changed in 3.5 billion years. We are beginning to change them in the laboratory, in synthetic biology. The reason is you want to create new molecules, put it in your body to fight cancer, but not get released to do something, do other damages. So we can take advantage of its convention, but it has all these properties. So one could try to understand how this came about. I'm not going to go into it because it'll take a lot of time. This is a paper in Journal of the Royal Society that we wrote. And that shows how the error tolerance and length of the amino acid, length of the proteins, can be controlled, and what kind of separating equilibria, local optimal, they can get stuck in. Okay? That itself is not interesting. The interesting thing is that you compare, if you are clairvoyant, if you are actually a designer, you could have done a lot better than what we have. The fact that we don't is a good sign that there's no intelligent designer. So if you are thinking that this was done by an intelligent designer, he would have done much better than what we have. Not significantly better, but definitely he would have found not a local optimum, but a global optimum. Maybe he's subtle but not malicious, so who knows? I'm not doing cybersecurity again, the good Lord, so I'm going to ignore that. If it was completely myopic, just Darwinian variations and selections, it wouldn't have come about. It would have been very error-prone and would have died. So we have something in between. But the other thing is that there was something that kept their utilities aligned. If that hadn't happened, they would have deceived each other. mRNA and tRNA would have deceived each other and would have not allowed this equilibria to come about. So what kept them together? The fact is they're cellularized. They're in the same cell. If they deceive each other, they both die. So their utilities got aligned by being cellularized. Right? So if you don't like the policies of your country, you build walls, you create a base, you tweet to them, and you cellularize. You go small. Right? So that's one way to avoid deception. You are Catalonia, you break from Spain, you are English, you do Brexit. So cellularization is one of the processes to get rid of deception. So the idea is that if two Catalonians deceive each other, they will both die an economic death. Okay, so I'm going to go fast. But this is very common. So there are some examples. We saw codons, and that's called Crick's frozen accident. An accident happened, it froze. Multicellularity, there is Cambrian explosion. Adaptive immune system, which is different in jawless fish and jawed fish. It's called immunological Big Bang. Sex, we have X and Y, birds have W and Z. That came through a neomuron evolution. And the idea of language and language organs and Chomsky's pop hypothesis. So it's only in one species it popped up somehow magically. And it's a conventional communication system. So let's go to internet. And I've argued that internet has lots and lots of signaling games. The game we play, we send a keyword to Google. We do not want Google to know our state of ignorance. We don't tell them that I have a PhD and this and that. I don't want Google to know that. But I expect Google to take an action, give me a good PageRank page that fills up my ignorance. Now, Google has a whole bunch of keywords and has a distribution that it doesn't want anybody else to know. And it sells them in ad exchanges to figure out which keyword goes with which ad. In the ad exchange, somebody wins the ad auction, and he has a product. He knows all the bad things about the product and all the good things, and he sends me a signal with an ad, and he expects me to buy. So all these three games are intertwined. So I can't break one from another. And if one of them breaks, if the ads break, Google dies. So does the idea of aggregating all the information. Does it make sense? So how do we go about doing these games? And how do we get good structures? The idea is that we want to introduce recommenders and verifiers, just as your question pointed out, so that it's distributed and the games have good equilibrium. So I'm going to talk a little bit about how to do these signaling games. So I want a system where the signaling games get implemented directly. So I have a programming language or some specification language where I describe the games, I describe the verifiers and recommenders. It gets compiled into hardware, crypto systems, whatever, and what I get is a well-designed signaling game that works. It's a bizarre idea, but why not? Yeah? So I want to design some senders and some receivers, and I want to design some verifiers, model checkers and miners, and I'm going to limit them. I'm not going to design Ethereum so that the systems are Turing complete and verification process is undecidable. That's asking for trouble. Okay, so I will stay with some sort of propositional branching time logic, and that's what the verifiers are. So it's limited. And for local things, I will use cryptography to do local verification. Yeah? And I will need asymmetric cryptography, so a sender and verifier can create verifying keys, which are their public keys, but they have a hidden keys, a private signature keys that they do not reveal to the whole world, and they are SGS and SGR. And the keys are linked by computationally one-way functions. I'm not going to go into post-quantum computing and talk about a verifier with quantum computers, factoring numbers. So we'll stay with just these simple assumptions. So sender generates a signature key and verifier key, publishes only the verifier key. Sender knows his own type, knows the message that he wants to send, and a timestamp. There's some way of a universal timestamp, so he knows when he's sending the signal. And he creates these tuples where the public key of the sender is concatenated with the public key of the receiver, concatenated with the message, and a hash of the type and the message, so that in the future, if he's asked, he can verify that he sent the message consistent with his type, because only he can hash. Okay. And a timestamp, and takes that entire tuple and encodes them using his signature key, using his private key. Since the private key is only known to him, nobody else can create this. Yeah? So what does the verifier do? So R ensures that that S sent the message because he has the public key of the sender. He can decode it and see that the senders and receivers are who he expects, and can check the local properties because the timestamp and the message and the type have to be consistent. So the hash function allows you to do that. But the checking the global properties, that over time it has actually done the right things sequentially, requires him to do some extra work. And he can't do that just from the message, so he needs some sort of database, some sort of a ledger that actually keeps track of this thing. So we'll call this a crypto ledger. Okay? And then once this is done, everything is verified, the utilities are revealed. So sender gets his utility, receiver gets his utility. So signaling game can be implemented in an abstract way. So I just said that once you have blockchains, but who will put the blockchain together? So we'll assume there are miners, but they are non-strategic, but they can be deceptive. So we'll use costly signaling. So we'll make them do some hard work to be able to be a miner, to be a verifier, and then we'll give them a proof of work, some computationally hard problems, so they will go to Mongolia and get free energy, free electricity, and do this. Is this clear? So costly signaling, proof of work, is necessary to keep them honest. So that's my full system. So So now we want to build something on this. So we want to create a group, and they will form a coalition, and there's a market maker, an intermediary who will develop contracts and activities among the people in that group while they remain anonymous. This is like a cellularization. So you join a cell, but you don't know who the other people are, but you can interact with them, and you're guaranteed that everything will happen in a truthful way. Okay? So the intermediary must not reveal membership information. The intermediary checks certain local and global properties about the players and publishes the results. So he does all sorts of temporal logic and model checking, et cetera, but he can't tell. He can tell if it is true or false. He can't give a counterexample. He can't tell who else took part. So it's a tricky way of doing model checking. So the trivial corollary, but if he is asked that what he says is true, he can do a zero-knowledge proof showing that what he says is true, but not revealing anything he knows. So you're guaranteed that his proof is correct, but you get zero knowledge about how he came about the proof. Yeah? So those are the ZK snarks, and they can be done easily with univariate polynomial identities or Boolean circuits. So I'm not going to go into that. And this was a talk to the finance people in New York, so you can see easily how to do a future or derivative or bond subject to positive and negative covenants, assuming that the covenants are written in a stylistic, limited expressivity. So I probably will run out of time, so I want to do this one game. So this I call monogamous endogamy game. It's very politically incorrect. So I have created a pool of people who are anonymous. I know their types. I know they're male or female, and they have two castes, maybe Brahmins and untouchables, and they have allelic types. So some are double mutants, so both their alleles are mutants. Some are heterozygotes. One allele is good, the other one is bad. Some are homozygous wild type. They're good guys. They have no disease. Okay? So this is sort of like a Tinder. So one anonymously within the group sends a marriage proposal or a dating to the other. And the intermediary checks that he only matches male and female. I know it's politically incorrect. Even politically more incorrect would be to he matches the Brahmins with the Brahmins and the untouchables with the untouchables, never the other way. And he matches, if the two players are homozygous, good wild-type alleles, he lets the marriage happen. If they're heterozygotes, he warns them. If they're homozygous mutants, he tells them not to marry because they will have children who will have the disease. Actually, there is a system like this for Orthodox Jews in Brooklyn. They get a number. When they go on dead, they dial in the number, and somebody looks up and says, if they go on a date, the kid will have Tay-Sachs disease, Crohn's disease, the whole cluster disease. So it has actually worked in reducing the cluster disease. Okay, so there's a marriage proposal. And then intermediary checks all these things and says when they are. But there is also one other thing. It enforces monogamy. So you can't marry more than once. So you can't do bigamy. So the number of marriages and divorces have to be even parity. So he has to actually go back, all the marriages you have been, all the divorces you have been, and has to count. So that's the simple temporal property, global property that he has to check. Of course, if you two people meet and they know each other and they marry, they can check that actually the marriage was determined correctly. But if the intermediary declines a marriage or declines every marriage, how do you know that he is not being deceptive? So one way to do that is when there is a unapproved marriage proposal, you can challenge, and he will give a zero-knowledge snark proof, and from that you can check that you had not been deceived. A declined marriage proposal is in fact a declined proposal. Okay? So Bitcoin is just a simple example of that system. The types are the Bitcoin wallets, and signals are encrypted messages, very similar to the one I talked about. Okay. And it has proof of work, and that's probably why it's working. But it is not really working when you go to Bitcoin exchanges, because you can't check as easily about the solvency of the exchange and there are lots and lots of problems. So it becomes interesting on how to design these truthful systems on top of Bitcoins like thing, ICOs. So there's a lot of interest. So that's, and there are examples in dark webs, Silk Road, Mt. Gox, and they can be all explained in this game theoretic setting. And we even thought about how to build a cloud with virtualization and meta-cloning, which guarantees all of these things, and also scales, so that you can have very large exchanges and will be operating in real time. So now you can think of designing a justice systems, designing a payment systems, designing a Tinder, designing via Uber. That does not require having a big cloud or a server, but you can rent things from there. So I'm just going through it quickly and then come back. So the hardware architecture looks something like this with a lot of virtualization. And it actually has a lot of very interesting hardware and computer science. And so some of the things that Intel has been doing fits very well. You can build it with existing hardware. I was going to talk about identity, but I'm going to skip that. This joint work with Will and Jose and 2 other people. But I'm inspired by this guy, Antonio Fernando Pessoa, who was a Portuguese poet, writer. He wrote in English, Portuguese, French, and he had 75 heteronyms. So he would write a poetry, and another person of his, a critic, will criticize the poem, and the other critic, another heteronym, will criticize the critic who criticized him. And he created this entire social network, fake social network, that was busy. He died in his 40s, but he's compared to Dante, Shakespeare, and Proust. He was a good writer. Actually, his book, The Book of Disquiet, just came out. It's a huge book. So how do you deal with this on the internet? I mean, I have nothing against Pessoa, but I wouldn't like everybody to be a Pessoa and write books and sell it on Amazon and give 5-star recommendations and then, right? So Sybil attack is a big problem, and there is a way to implement this with the machinery that we just talked about. So, and there are lots of simulations of evolutionarily stable games, and shows that with verifier recommenders, it comes back to stable organization very quickly. So that's something that's interesting, and there's lots of things on how cybersecurity is approached here, what it should be in the future. And I want to leave a puzzle up, which I call Pawn-It game. So this is about ransomware. So it's an interesting puzzle. There's some of the things that are coming out in AI that's beginning to touch on game theory, fits in very well. There are finance systems built out of agents, but I think it's a general problem. It's not just a cybersecurity problem. This problem comes in understanding cancer and therapy design, multicellularity and aging. Internet has lots and lots of examples, economics and finance systems with dark pools and high-frequency trading. Many of these questions come up. And of course, governance is a great example. It goes back to Socrates, who thought about a philosopher king who becomes a tyrant, and tyrant leads to aristocrats. Aristocrats becomes oligarchs. Oligarchs leads to politia. Politia becomes democracy and mob rule. We seem to be going through shifting to both tyranny and oligarchy and mob rule simultaneously. So Socrates couldn't figure out how to fix that. And Aristotle wrote about this, but the people who figured this out are Polybius and Machiavelli. They came up with this idea called mixed constitution, which has 3 systems. One is the executive systems, which is the philosopher king. The other one is the judicial systems, which is like aristocracy. And the legislative systems, Congress and Senate, which is like the politia. And with checks and balances, they're supposed to keep it in a good equilibrium. But there are other institutions like Muse. The news has become fake news. So we have an interesting question here, how to think about governance, but also how to think about governance within internet. So, so I hope this is just a conventional end. We'll think about it and have questions, and we'll go on. This is just the beginning. It's not the end. So thank you. No question? Yeah?
Do you have some citations for the papers that this
Yeah,
presentation?
yeah, not on the slides, but it's on my webpage. Also, quite a few are with Will Casey and NCI. The biological ones are somewhat different, and there are some in finance. So I gave a talk on that on Friday, on stress testing and things like that. Money laundering, so there is, it never ends. So I'm not going to be unemployed for a long time. There's enough deception to go around. Okay.
I have one question. How do you consider the time dynamics issue of this descent?
Right. That's a good question. I mean, all of this is assuming the types are fixed. There's no type fluidity. And the utility functions are fixed. So if you're a good guy, you are a good guy forever. If you're a bad guy, you are a bad guy forever. So what happens if there's identity fluidity? And that is very hard to check because there are lots of Bayesian games and there are Bayesian biases. The best example would be Amazon just announced that they will be loss leader even for other people who sell on their sites. So they're going to give you discounts and lower the price and wipe out all the other competitors. So they are good guys now, but they are being loss leaders, so someday they can price you whatever they want. How do you model those things? So it's a deception that hasn't happened, but is preparing to happen. I don't know the answer. Bayesian bias are very hard to, and repeated games are very hard to counter.
But your model already have timestamps, right?
Right, so there are timestamps, but this requires assuming what the intentions are, what they will become eventually. So sort of like a zero-day attack. You don't see it until you see it. So there's no timestamp, there's no blockchain for zero-day attacks. I don't know the answer, but these are very good questions. I mean, we do try to address this by antitrust laws, monopolies, insider trading, putting people in jail for having 3 passports. And so we do a lot of things. But we don't have a very good argument of why those things work, because that requires you to anticipate how they will be doing the bad things in the future and how we are interacting with them, right? No? Okay.
Thank you very much.
Thank you so much.